Okay. All right, so I got almost finished my master's, but I got my master's basically more in the digital logic design and low-level embedded software. So that's kind of what my stuff is about, is embedded systems and low-level software. I don't do too much of the web dev stuff, but hopefully this will be interesting to some of you, at least not informative. This is kind of a way to give you a brief introduction into what FPGAs are and how it applies to software as well. Again, this is cramming about 5 years worth of information into 20 slides. So there's quite a bit of information here. A lot of it will be just background to understand what an FPGA is, and then we'll get into how it applies to software. So have any of you besides Dallin heard of what an FPGA is? You, okay. We got one person besides Dallin. So we got two people. So FPGA stands for Field Programmable Gate Arrays, which is basically a logic chip that you can program to do anything you want, but it's a physical circuit. It doesn't run software, and we'll get into why that's cool and why it's an awesome field. I love it. It's not for everyone. Basically, the pro tip with FPGAs is you have to learn how to count to 1. You just got to do it at the right time. If you don't, then things don't work. So we'll get into it. So FPGAs are physical chips that are reconfigurable. They're basically like a transformer that can shapeshift and turn into anything you want it to be. But they are not a CPU. They are not a GPU. They don't run software. The development time to build a design is extensive. It's very hard to build a design. It takes forever. It's a lot longer than software. But basically, it's a chip that you can program hardware into, and we'll get into how that works. So that's basically what FPGA is and is not. So some of the use cases for FPGAs is they only cost anywhere from $20 clear up to $20,000 for a chip, depending on what you need. But they're really good at being a prototype chip. If you don't have high production volumes, say under 1,000, FPGA is the way to go rather than trying to get a custom chip manufactured, which would cost millions. So you can prototype architectures, protocols, digital interfaces. You can connect two different peripherals that can't talk to each other. You can make the digital interfaces connect to each other by translating each other's calls. And then they offer a lot of flexibility. Like I said, they're like a transformer. They can become anything you want them to be. And this is an image of what they look like. They don't look too interesting. They're just a generic black chip. But what they can do on the inside is really cool. So you can integrate software, offload computations from the host to the FPGA, and you can speed up algorithms like in software. And another cool thing that we'll look at the very end is how you can use it to emulate old deprecated hardware that you can't really buy anymore, and still run those old vintage games and whatnot. Just a brief overview. The top image is what a CPU die looks like. It has dedicated hardware, cores, cache, memory controllers to execute instructions, your software programs. On the bottom is an FPGA, which just looks like a generic grid, and that's exactly what it is. It's built up of a bunch of logic elements, and you basically connect all those circuits together to do anything you want it to do. So there's basically 3 main elements that make up FPGAs, and we'll get into those building blocks, but that's what the die looks like. It's kind of cool looking.
So you've got a bullet point there. I've never worked with FPGAs, but you say that the cells contain lookup tables, muxes, and registers. Like an individual cell can contain all of that?
Yeah, so it depends on the manufacturer. Like Xilinx, which is owned by AMD now, refers to it as a logic slice. And each logic slice contains 2 of these things, and we'll go into more detail of those. But Altera, which is owned by Intel, calls it a logic element, and each manufacturer has its own slightly different wording. But yeah, each cell will contain at least one of each of these things. Yeah. That's a good question, and feel free to interrupt me if you ever have questions. So these are the 4 main components, which is a lookup table or LUT, BRAMs or block RAMs, muxes or mutexes, and then registers or flip-flops. Those are the main basic building blocks. So basically a lookup table has inputs that come in here, and then as a single 1 bit of information that comes out. And that, again, this is FPGA engineers are concerned about things in the order of 1 bit of information. So you have data that comes in, performs a lookup on that data, and then you get your output. And then muxes are pretty simple. They just simply select, let me get the laser pointer out. But they simply select between these two data lines and put it on the output based on the select line. It's basically a way to select data. And then block RAM is kind of just the way it works on your computer, just smaller. Instead of being gigabytes, they are literally a couple of bytes to maybe a kilobyte at most. They're very small memories, and they're distributed out through the FPGA. You couldn't group all of them together to be one big block RAM. You have to use them individually. You can route a few of them together, but again, they work just like RAM, like on your computer, just smaller. And then the last thing that really makes up the FPGA is registers. So registers have a clock signal that goes in, and when the clock's high or low, it can set the inputs and outputs, and it holds 1 bit of information. So again, you have to learn how to count to 1. Is it on or off? So we're going to get into a little bit about architecture, what those cells mean. Again, this is just a brief overview so that we kind of understand what an FPGA is before we go into the software. This is what the chip looks like in the planner. It has what's called the clocking regions. We won't go into that, but that's what all those tiles are. But over here, this blue section is the part that was utilized by my design, which is a small portion. This FPGA right here costs $100. It has 35,000 of those logic elements, those cells, and that's kind of on the low end. If you go up to like $10,000, you can get over 1 million logic elements in them. So if we keep zooming in, we can see a little bit more detail, and now we're starting to see those little cells. So we'll zoom in one more time. Right here, this blue one that's highlighted is used, and this thing right here is a slice. And inside of that slice are 4 lookup tables, 4 flip-flops, and a bunch of muxes. But this right here is a lookup table. Inside of here are some muxes, and then these little squares are flip-flops that store 1 bit of information, and then this big block out here is those distributed block RAMs. And so basically, you write code that describes hardware, and the compiler will turn it into the physical circuits. And so you always have to look at your code and remember it's not software code, it's describing a physical connections like this. So again, there'll be about 35,000 of those cells to millions of these cells.
And the compiler takes care of setting all that up for you?
Yeah, it does. You can get down to the nitty-gritty. You could click and drag each individual wire if you wanted to, but it would take your whole lifetime to do what this can do in an hour.
Yeah. Okay.
Yeah, but you have that control if you want it. Yeah, don't recommend it though. There's one other block that some FPGAs offer if you go up just out of the bare bones, just a step up above that, which is by some manufacturer called a DSP block or digital signal processing block. It includes hardware to do multiplies, adds, divides, and pattern matching and accumulates. You could implement that with those lookup tables and registers, but it would use a lot of resources. So instead, they give you a physical multiplier rather than using up all the resources for just that. And we'll show an example of that later. So the design flow has quite a few steps. The first design is, well, first have an idea. You draw what's called block diagrams. We'll see an example of that. You design the data flow, how data comes in and how it gets to the outputs and how it needs to mutate it or what it needs to do with the data. And then from there, you start to write your code. And then from there, you do what's called synthesis, which then takes your code and turns it into some of those abstract elements like the lookup tables, the flip-flops, a bunch of other digital logic, generic gate representation of it. And that produces what's called a net list. It's just a list of all the components of the design, but it's not tied to any specific FPGA. Then you go into what's called implementation, which does what's called placing and routing, which is exactly what it sounds like. It places the design in a physical FPGA and then routes all the signals to all the different registers, lookup tables, does all that. And it's what's called an NP-complete problem, which means it can be solved in polynomial time, which means it takes forever. So if you did a hello world application, which is blink and LED on and off, that will take 5 minutes for it to compile. If you do a design like I do at work, it takes 13 hours. So it takes forever. If it gets the design wrong, like it doesn't meet timing, it has to rip up the whole design and try out a new layout. And it uses an algorithm called annealing. I don't know if you ever heard of that, but it's a way to try to guess what the best solution is.
Can you speed it up by like buying a bigger computer to do the problem?
It is parallel, so the more cores you have, the better it is.
Okay.
And you can do things where it won't try to find the best solution. You can just say, I want a fairly good solution.
Okay.
And again, with these FPGAs, you don't need the exact best solution. You can get away with an okay solution.
Okay.
Yeah. So again, it applies timing analysis. It just looks at, okay, will this signal get from point A to point B in time? If not, then it fails to meet timing, and you can do things like add another register so it can save it in the middle and then send it off later, or you reroute things and try to meet timing.
Did you specify the timing or?
To some degree, yeah. So you specify like all the clocks, how fast they are, like 100 megahertz, 50 megahertz.
Sure.
You have a bunch of those signals, and then it will try to make sure that the signal will arrive to the other place in one clock cycle.
Okay.
If you're okay with it arriving multiple clock cycles later, or you don't care when it arrives, you have to specify in your constraints file that you don't care.
Okay.
Yeah, but for general, it will try to make it match for every single signal in there, and there'll be thousands of signals. Yeah. And then finally, if all that works, you get what's called a bit stream, or for all intents and purposes, a configuration file that configures the FPGA into that hardware that you want it to be. So you basically can think of the config file as a circuit breaker in your house. The config file tells which breakers to be on or off, and it connects different circuits in the house, basically. That's basically all the config file does. Yeah. So there's two main languages.
I've got a question
Yeah.
about that. Maybe you'll get to it later, but at the beginning you mentioned that it was reconfigurable, and I'd only ever heard of FPGAs in terms of burning out gates, which was a one-time operation. Maybe that's old or cheap. Or
Yeah.
I don't know.
So
Can you actually like go back to a chip that you've already configured and completely change it to something else?
yeah, you can do that on the fly as well. That's a little bit more complex topic, but some of the original FPGAs used to be one-time programmable. They are called CPLDs when they first came out, and they're very simple. And they would have like electronic fuses that you would burn permanently, and they were one time. Some microcontrollers are still that way these days, but field programmable implies that out in the wild you could reprogram it, reconfigure it, and you can do that as many times as you want. In the FPGA, it is volatile, so that configuration's loaded. As soon as you lose power, it loses everything, so you have to reload that config file every time you power cycle it. So
What does that take?
under a second.
Oh.
It's really fast. Yeah.
So that would be part of your firmware or something.
Yeah, so you'd have a little flash chip apart from the FPGA, and when the FPGA gets power, it looks for that device and loads it in. But the memory will be external, except for Altera. Some of Altera's offer internal flash memory, but it still loads it on power up. Yeah. Answering your other question, sometimes if you do very special design, you can have certain areas that you can just rip out while it's running and place a different block in there while it's running. So if you want to do one algorithm and then you need to switch to another one, you can do that. But that takes a lot of design and consideration, but it is possible.
We used to do that back in the days of DOS. We had limited memory, and sometimes we swap something out.
Yeah.
Back in
So
pain.
where I work, we have a limited FPGA. We don't have enough room for everything, so we actually swap it off based off of what we need it to do. Yep, and like you said, you run out of room. So instead of being memory, we run out of physical gates. So in industry, there's two main languages. Each of these are about sometimes 40-60, sometimes 50-50. Basically, they're both widely used. VHDL is more professional and in the defense industry. Verilog is a little bit more in the open source, but it's still a pretty even mix. Some people say you can do certain things in VHDL that you can't do in Verilog. I have yet to see an example of that. They do the exact same thing. The syntax is just different. VHDL enforces data types a lot more. It's a lot more strict. While Verilog is a lot more relaxed on the enforcement of types, it relies on you to catch those things. But basically, this is what's called a module. You also can mix and mix these languages. It doesn't matter. You can integrate all of these together. It doesn't matter. It's like mixing C and C++. It really doesn't matter.
Which one do you like best?
I'm now kind of used to both, but I still like Verilog because it's just so much easier to type.
And if you were a beginner and you were interested in checking this out?
Verilog.
Verilog?
Yep. Yeah, I would choose Verilog because it looks kind of like C. It looks like other programming languages.
Right.
VHDL kind of looks like Ada, if you've ever heard of that. Yeah, so it's kind of like Ada. It's a different beast.
Yeah, it is.
So basically, you just have some statements. There's two main things in Verilog, a wire and a register. Register is kind of like what we talked about. So if you ever see reg, that's referring to a register. And you can have an array of registers. And a wire, I don't have an example here, but a wire just takes a signal from a register and routes it somewhere else. And it doesn't remember anything, just like a wire in your house can't remember anything. So you can just do, this is basically a counter, but it's the same thing implemented in both languages, just so you can easily compare it. And that's basically it. There is another language called System Verilog, which is a superset of Verilog that is like C to C++, where they add a bunch of features on and do a bunch of different things. But a lot of that is for what's called simulation, and we'll go into a simulation a little bit. But I won't talk about System Verilog too much because I don't know it as well, but just know that it is out there. So, skip 2 slides. Okay, so there's two main types of logic design, which is combinational and sequential. Combinational involves no clock signal. It's just the inputs go through gates, and then they propagate to the output. They do not store information, so once the inputs change, the signal propagates to the end. Sequential logic has a clock signal. Every time the clock changes, it adjusts the outputs according to the inputs, and it synchronizes everything. So your CPU in your desktop or laptop has a clock signal. It controls everything. It makes it a lot easier to test and develop when you have a synchronous signal rather than asynchronous. But you need both of them in FPGAs to do things. So this is an example of a combinational circuit. It's just an AND and OR gates, just like you know in programming you have AND and OR operations. Same thing with digital signals. Basically, you have an AND gate here, it goes into this internal wire, and then we AND that again, or we OR it, and you can see the two AND gates and the OR gate. That's really all there is to say about that part of it. And again, the important thing is when you look at HDL, which is hardware description languages, it's not code. It's not like it runs this statement, then that statement, then that statement. It's a physical circuit that operates in real time. So everything you know about software, you got to throw it out. Here's an example of sequential circuits. So basically, we have two registers here and here. So the output register is this one. The intermediate register is this one. And we have what's called an always block. And it just tells us on the positive edge, or when the clock goes from low to high, I want you to do everything inside this block. So both of these statements happen at the exact same time. It's not one then the other. It's the exact same time. Why is that? Well, because a physical circuit doesn't care about sequential stuff. It happens in parallel. Both registers update at the same time. So it takes a while to get used to that. But this signal right here, these two right here would be the in1 and in2. And this would be the output of the AND gate. And then this spot right here would be the data in the register right here. And then this last register would be the output. But you can see how it's been delayed 2 clock cycles because there's 2 registers as to propagate through. So that's a sequential, sequential logic. And then there's one other design principle that's used a lot, which is called finite state machines, which is basically these bubble diagrams. And this happens to be kind of like a timer state machine. And it's a very useful way to describe your logic because it's really easy to look at this diagram and know what it can do and where the data, how the data relate, or the inputs relate to the output, and how it can go from one state to another. And imagine trying to design that with AND gates and OR gates. It would be a nightmare. So using, it's kind of small text, but this is the case statement that has all the bubbles. Each case is a bubble in this diagram. And this is a lot easier to write and maintain than doing it from the ground up with simple logic gates. So state machines are really important. They're very useful. They're a lot easier to write and debug. So just for reference, if you were to look at the implemented design, it looks like this, which doesn't make much sense, but it makes sense to the computer, and it operates exactly as that bubble diagram does. So the last thing is, how does a lookup table implement all your custom logic and operations you want to do, like if statements and other operations? So if you have an equation like this that's A and B or C, the computer will generate a truth table. And it's basically a kid that studied for the test, wrote down all the answers for the test, saved it into memory, and when he sees the question, he just gives you the answer without calculating it. So the FPGA uses those lookup tables. So whenever you get A, B, and C on the inputs of that lookup table, it just performs a lookup table into that memory and pulls out that single bit of information. So that's how it applies all those if statements. So you say, if this is high and that is high, then set this one bit high. And that's how it does it. So it's not too fancy. It's not like it morphs the transistors into different things. It just has those lookup tables. So one of the great ways to document your FPGA stuff is to have waveform diagrams, which is just basically a visual representation of the timing of signals. It just makes it a lot easier to read and understand how they relate to each other. Because you look at the hardware description language or the code, it's hard to figure out exactly how that's going to perform or operate. So having documentation like this makes it a lot easier. The last part is simulation. And if you remember that design flow, how you go design, synthesis, implementation, and bitstream, with simulation, you can do a simulation at each one of those steps. So, because the synthesis part might take less than an hour, and then you can run simulation on it. Or even before synthesis, you can run simulation on just straight the VHDL code that you wrote, which is a lot faster than waiting 13 hours for your design to compile. Simulation allows you to look at all the internal signals. It's a simulation of it, so you can look at every signal that's going through it. If you were to put it on the board, you'd have to take a wild guess at what's wrong. So this allows you to peek inside. And with my senior project that I did, I spent 4 months simulating it before I even put it on the board. And then when I put it on the board, it worked the first try. And that's what you try to shoot for, is simulate way more than you need to, so you don't have to try to debug a physical circuit. That's not to say my design was bug-free, but it did at least do the operation. So, and you can also write test benches in such a way that they don't match what would happen in real life. So just like with coding software, if you write poor code, it's not going to do well. So you have to be careful how you write your test benches. And then I'll just cover all this really quickly. You can do what's called high-level synthesis, which basically can take certain portions of C and C++ code. You have to add special compiled directives. But it can unroll your for loops and offload a lot of that digital design on the computer, and it will generate the hardware for you based on your C++ code. But it's not like you could take a whole entire program and chuck it in there. You got to tell it which for loops, which chunk of logic you want to implement in hardware. And it's pretty tricky too. It's still not trivial either. But yeah. And the last little bit is they have what's called a microcontroller and FPGA, and I have one here with me that we'll look at. But it basically has a little ARM microcontroller that runs, C, C++, and then around it is a FPGA. And so you get the benefit of both worlds of having software and the hardware right next to each other. They can talk really fast. And the only really downside is it costs a little bit more to get one with both in it. But the yellow thing is the FPGA, and the inner box is the microcontroller. So that's an option. And you can use each one completely independent of each other. So at the very end, I'll have a demo of these. But this was my senior design for my undergrad. It's a logic analyzer. I don't know if you've ever heard of that, or an oscilloscope. But basically it allows you to record digital signals and then analyze them later. So the main reason I use the FPGA is because I can take in anywhere from 8, 64, 100 inputs all at the same time at a very precise interval and record those. If I were to do that in software, the software might get an interrupt for some service routine, and it would have incorrect timing, and it wouldn't be evenly spaced. So the FPGA allows me to do all of that in parallel, all at the same time. And again, all of these blocks are running in parallel, all at the same time. There's no sequential stuff happening. So basically, the data comes in, it waits for the condition that you want to record data, and then it saves it off into a buffer, and then it has a little finite state machine that controls all this, and then it has something to talk to the computer, and then all that data gets offloaded out of the FPGA into the software application, which I'll show you later. And this is kind of what my GUI looked like. These are the digital signals that it recorded. You can see that it's kind of changing. But this GUI, I threw it together in 2 weeks before the senior project was due, so I spent most of my time on hardware, so don't judge the GUI too much. But it did work at least. But yeah, so that's kind of where we're starting to dive into where the software connects to FPGAs. One of the other things I'm working on right now, unfortunately I didn't get it done in time, but is I'm taking in analog audio data, and then I'm running it through what's called a fast Fourier transform, which basically allows me to break out the treble, bass, and mids. And then I offload that data to a microcontroller, which hosts a web page that allows you to see that data, and then you can adjust the treble, bass, or just completely cut out frequencies. It sets a bunch of control registers, and then it will output the audio again without those frequencies. And so you can filter out the bass or treble or whatnot. So that's kind of how software can tie to it, and the hardware does all the hard computations while the software just reads it and displays it. And so my GUI or my web page isn't that good, but this in the early stages, but it would look something like this, where you have the switches where you can control the frequency bins, and it displays you the amplitude of each frequency. Yeah. So I'll show a live demo of this at the end, but this is what it looks like. So this pi demo calculates pi by generating a bunch of random numbers, and if it falls inside of a circle, it adds it up. If it falls outside the circle, it divides by that number, and you can get really close to estimating pi. It's a horrible way of doing it, but the point is it's the same algorithm in hardware as it is in software, generating random numbers, adding them up, and dividing them to try to estimate pi. So again, I'll do a live demo of this, but this right here is the block diagram for the hardware, and each of these boxes is a processor, so to speak. It's doing the multiplies and adds and accumulates and does some of the other calculations, and then it loads it back to the processor so the processor can view it. But in hardware, it did over 4 billion calculations in 0.85 seconds, and the software did around, I think that's 500 million or 50 million samples in 9.5 seconds. And it's not even close, So if the processor were to run to the same amount of samples, it would take 13 minutes versus 1 second in FPGAs. So now you can kind of see the benefit of offloading your algorithm into hardware. It's because you don't have to execute those instructions sequentially. You can do a lot of it in parallel. One of the other things I can do that probably make this a little bit more confusing is I can turn an FPGA into a CPU. I can design the architecture for a CPU in what's called a soft core processor. It's not there physically, but it's a soft core. And the cool thing about doing that is you can have a soft core, and you can make custom instructions and custom peripherals to that processor to do custom things. That's used quite a lot in industry as well. And And it's a great way to test out new architectures or instruction sets. I don't know if you ever heard of RISC-V. Instead of being ARM or RISC or x86, there's RISC-V, which is open source. You don't need to license it. And a lot of people implement that into FPGAs to avoid, the licensing fees of using ARM or other things. Yeah, and that's the instruction set that it uses. If you ever know assembly, that will make sense. But yeah, we wrote Python that would take that instruction set and compile it into a hardware description language so we could use those opt codes. And then we also wrote a Python interpreter that would take the assembly code that we wrote and then turn it into a binary file and assemble it that we would then load to the FPGA, which would then execute the code as if it was a processor. So the FPGA can run code, but the hardware itself is not running code. And then the last thing is what's called the MR project. I have nothing to do with this. This is an open source project that you can go and experiment with. This board is, I think, around $200. But basically, it has a bunch of cores that you can load onto it from an SD card. And it allows it to become an arcade machine, NES, a Genesis, Atari, many more, Commodore 64, whatever you want it to be. There's a lot of cores available. And basically, you can get your old game ROMs, offload them to the SD card, and then have this thing load them and plug in an old PS2 controller and play your old games from the 70s and 80s and 90s. And the software doesn't need any changes because as far as it's concerned, it's running on original hardware. So that's one of the other cool benefits of FPGAs is keeping these old games around. That's one of the cooler projects out there. So I'm basically going to end the slides and then I'll show a little demo of one of the FPGAs. I'll actually have two demos, but so this one right here has the microprocessor and the FPGA in it. There's an Ethernet port, USB port, and it has 0.5 GB of RAM on it. And so we'll just see that same Pi demo in real time is basically what we're going to do. So now if I just push the reset button, so the hardware's running, hardware's done, and I have the software limited to 10 seconds because we don't want to sit here for 13 minutes. Hopefully it's done pretty soon, and there's the software results, and you can see the software takes a lot longer. So that's the real-time demo of that estimation of Pi. Again, the hardware did almost 4.3 billion, while the software did around, I think, 50 or 500 million calculations, so it's quite a bit more. And then the other one will be the logic analyzer demo that I kind of showed some of the slides from my senior design. So let me get that one out. So this board is a lot smaller. Let me get it out. And so it's a lot smaller, a lot thinner. They both actually have the same amount of logic gates each other. This one just had the microprocessor. And we're going to add a little ambient light sensor, and we're going to view the real-time data as it talks to back and forth. So I'll just slot that in there and then plug this in and we'll get my Python code running. Let's see. Just give me a second to open. I should have had this open, but my laptop doesn't work well sometimes. So, come on. And then let me just set up the config because I think it's wrong. I have no idea what COM port this is. 1 second. Yeah, this one will be each
one gets a new one?
Yeah, it's just the way Windows handles it. I said 10, right? Yeah.
Yep.
Okay, this is just some config stuff for the GUI, but let's see. Hopefully it works. I tested this last night and it works great, so hopefully it works again. So yeah, I'll just tell it to start capturing and let's hope it works. So it says it's captured something, so hopefully it works. Usually it doesn't take that long though. Oh. Yeah. Of course not. Okay, I don't know why that took so long, but it's usually a lot quicker than that. I think it's because I'm oh, I know what it is. I'm sampling too low. Okay, hold on. Let me relaunch it. I forgot to change this to a 1. That's the sample rate. I don't need to be that slow. Okay. Yeah, it's already reading. Now it's loading it. Come on. What does it say? Of course. So, again, I should have spent more time on the GUI. Yeah, there we go. Okay. And I forgot to bring my mouse, so cross your fingers, I can actually zoom in. And this is about 1 second of real-time data, just for reference. I hope I can zoom in well with my mouse or trackpad. So yeah, this data is saved in the FPGA, and then Python pulls it from a serial port in a separate thread. And it also sends commands via Python via a serial terminal. And the red line is where it triggered, where it decided to capture data. That's what the red line is. It has a pre-capture buffer. That's how it got data before the red point, and then the red point is after the trigger. So basically, you can see the clock signal, and you can see these data right here. And then this is just what's called a chip select. We won't go into that, but basically this part right here is the data, and this right here is the clock signal. And now you could decode it and analyze it and make sure it's talking correctly to other devices and whatnot. And this graphing is just using matplotlib with Python. So, and then what we can do is we can just click on it, and then it will tell us here in the bottom that is 500 nanoseconds that thing was high for. And you can do other analysis. You can do protocol decoding. But yeah, that's basically FPGAs in a nutshell. So I don't know if there's any questions.
So you did your master's and you're now working in the industry.
Uh-huh.
What type of job? What's your job title? And is this the kind of stuff that you do all day? You're just trying to. Someone says, and what problems are I understand some of the problems you outlaid, but like what problems are like. It's a complicated one, but what problems are you like? When would I got signal data? Like what else would? It looks like you do just about anything, but I mean, what's the main? Like I'm going to hire you to do work, and what would I hire you for?
Yeah. So answering your first question is, I'm a computer engineer, which is a balance of hardware and software. So, but at work I have a software engineer title. But there's other FPGA engineers at my work that have an electrical engineer title or an embedded systems title, is usually what the general titles will be. It falls under a lot, just depends on your company. Sure. But yeah, FPGAs are used in a lot of industry, defense, space, automotive, audio signal processing, real-time processing like AI for cars, self-driving cars use FPGAs. And so for autonomous cars, you'd be taking in video data and then performing edge detection and see where the ends of the lines are or whatever.
Sure,
yeah.
Okay.
You can
do that in hardware because it's going to be super fast.
Yes, it'll be a lot faster than trying to do it in software.
I need that when you're driving it. 70 miles an hour.
Yeah, you don't want to decide you want to brake a second later.
Sure.
And then the caveat with FPGAs is the learning curve is huge. The cost can be more than software. The power consumption of the chip is higher than a dedicated chip. Like if you were to make it a microcontroller or a CPU, it will be less power efficient than a dedicated CPU, obviously. You know,
Sure.
it's just running a language through an interpreter rather than a compiled language.
Yeah.
Just more inefficiencies. But they're still a lot of fun. They can do a lot of hard work. They're used, again, automotive satellites to integrate sensors, again, audio applications, other signal processing of real-time data, where you need the results really fast and at precise intervals. And if you need to do a lot of parallel processing, they're really good at that.
Could you put a whole bunch of them together and build a neural network?
Yeah, so some people use FPGAs for machine learning. They're not quite the best, but they do make some special FPGAs that have big chunks of what's the multiply blocks to do all those calculations for matrices.
Sure.
They aren't the best, but they're still fairly decent. You can find a lot of libraries out there to do that. But again, the learning curve is huge. It's not like just software, you can just write it. It's a lot of understanding of how it relates to physical hardware. But they are getting there to where it's more of a software side of things.
Neural networks, you do so much of the multiply and add that really all you want are those cells.
Yeah, that's
for
what
the DSP. So
Yeah.
a lot of people will use DSP chips instead of FPGAs.
Mhm.
But also GPUs are multiply add, same
Mhm.
parallel
Yeah.
levels.
Yeah.
So that's why GPUs are used.
Okay.
Yeah, so if you want to go the machine learning route, GPUs are the way to go. At one point, when crypto mining was a little bit easier, you could have an FPGA do it really well compared to a CPU. But now the hashing is quite a bit harder, so now you need a dedicated miner to do it, really.
Sure.
But at one point, they did use FPGAs quite extensively.
Okay. That's awesome.
Yeah.
Some people also programmed like hash and encryption algorithms into FPGAs
Yep.
to do password cracking
Mm-hmm.
because you can go through more hashes quicker on an FPGA than on a normal
Sure.
CPU.
Yeah. Also, if you wanted to take like HDMI signal and convert it to DVI for some reason, you could do that in an FPGA. And and again, it's really good at doing real-time processing. So.
So, kind of related to that, what applications are there where FPGAs get outstripped by other processing things? Because we talked about some areas where you'd want to use a different processing setup. What are some of those applications? What are some of those things?
Well, for sure, if you have an agile environment, you don't want to use FPGAs. If you have like web hosting, web pages, all that stuff, FPGAs aren't going to really do you any benefit. It's more of a niche thing. Again, development time will be a lot better in software. Software you can run a lot of nodes. You could chain a lot of FPGAs together, but why do that when you could have a cluster of CPUs? It just depends what you're doing. A lot of it can be done in software, and software is fast enough. It's really when you want that real-time processing or very custom logic to do a very custom algorithm or encryption, or just make two old pieces of equipment talk to each other, or a thing where you have very low volume, a very select small customer base, and you want to provide them hardware that you can update later down the road and fix bugs without having to remanufacture a whole new board. You can just provide a configuration file and they're up to date. That's one of the big benefits of it.
And when you talk about doing algorithms on the FPGA, it's pretty small algorithms. When you look at, like on the small side, the 35,000 gates in the
Mhm.
array, that's not a lot of room for general programming
Yep.
stuff.
Yep. Yeah, with 35,000, you'll start to run out of room. Again, when you get into like the industry, this is more the hobbyist level, but if you get in the industry, you can get into the 250,000 to 1.5 million logic elements, which can run a lot more. But even then, with machine learning applications, you can run out of room. Yep. So, yeah. Any other questions?
So the board that allowed you to play all the older games, that just want to do NES and it just swaps to a different config.
Yeah, you just tell it. It has it's like this board where it has a microcontroller and a FPGA, and you just talk to it via Linux, and you just say, hey, load this FPGA image or configuration file, and then it will reconfigure into an NES. You know.
And then this runs with all the correct timings, and that's
Yep.
all specified in the computer. That's really cool.
Yeah, so it will.
They're emulating the original CPU, the original
Yeah.
video chip, the original sound
Yep.
chip,
Yeah.
the original.
Everything,
Yeah.
all the buses.
They're not emulating it, they're actually running.
Yeah, it is. It's a hardware. Yeah, when we say emulation, we mean a hardware emulation, not a software emulation.
In
Yep.
fact, it's a better emulation than writing something to
Yep.
run on a CPU.
Yeah.
Yep.
You got all these weird, like, you get the timing. Yours is so much faster than the original
Yeah.
Nintendo.
So with that, that Mr. project, it emulates clear down to the weird register that's often some weird location of the CPU, and it implements that weird instruction that no other processor supported, and you can.
They cause some random
One
game to
game
not work.
uses it.
Yeah, and one game uses it, and back then that instruction actually had a bug in it. That actually happened on a Commodore 64. One of the pets or one of those had a hardware bug in the CPU. But yeah, so that's one of the cool projects, and that project is a lot more user-friendly. You don't have to know as much about FPGAs. They have a lot of documentation. Basically, it's one of those things, it's already packaged for you. You just have to load it on there. So that one is, if you want to play around with retro gaming, I would get that. Or do a RetroPie, so.
Is there, you talked about the simulation step. I'm assuming that's running on the computer?
Correct. So the software simulation is just that. It is a sequential simulation. It tries to evaluate it as if it was running in hardware, and it emulates how it would behave in hardware, but it's not always accurate because, again, it's running sequentially.
Right.
So it's got to update everything and then say how would that then update to the other registers if it were in parallel.
Sure.
Yeah.
Sure. Okay.
But yeah, it is a software simulation. Yep.
And that, you said that's like fairly accurate. Is there big deviations in that where if I'm doing
yeah.
something and I'm doing X, then I know that I'm gonna have to burn this onto the, or not burn it onto the hardware. Sorry, that's not the right word, but configure it onto the hardware. Right?
Yeah. So if you write a test bench and you don't emulate the inputs very precisely, and you think their inputs are synchronized but they're asynchronous, that can get you into a lot of trouble.
Okay.
So you just want to make sure that your data that you have coming into the test bench is representative of what it will actually be. And some of the design constructs you can do in the software simulation basically lets you get away with murder. It's just bad coding principles with any other language. You shouldn't do that. Python, you can do this weird thing, but really you shouldn't,
Right.
Yeah.
That makes sense. And is Visual Studio your primary editor, or do you have some specialized software that you?
Excellent
company purchases?
question. So each vendor, like Xilinx and Altera, and then there's another one, I forgot the name of it. I wish I could remember, another major company, Lattice. Each of them have their own IDE, and you have to use that because the tool chains are closed. You have to use their tool chain, although Lattice has a few open source tool chains, and you can use any IDE with your own tools if you want. But the Xilinx and Intel ones, you have to use their tool chain. You can write the code here in VS Code like I have done, or in Emacs or any editor, because it's just text files.
Sure.
But to actually do the compilation, you have to do it in their IDE or via the command line via their tools.
Okay.
Mhm.
So when you say Verilog is more open source, what part of that is open?
Not that Verilog is open source, but it's used more in open source projects.
Oh, okay.
Yeah, because it's a little bit more beginner friendly and simpler. Mm-hmm.
Okay.
Yep. Sorry, I might have phrased that poorly.
Did you have, when you first started learning this, was it hard for you to transition between the two, or did you get it pretty quick? I'm asking more along the lines of, like, if I'm thinking Python, I'm thinking this particular way, I'm writing Python code, but the idea of thinking like everything's running at the same time seems like kind of a big gotcha.
Yeah, if you're coming from the software world, looking at HDL, like, I don't know, let's just look at this. What does this even mean, right?
Sure.
It's a whole different mindset. Everything you know about software, you should just throw out when it comes to HDL and look at it from a different view. Is that this is describing hardware. It's describing how data flows through registers. It looks like software, but it behaves nothing like software.
Okay.
And the learning curve from Verilog to VHDL is not too much. a lot of the same principles and concepts carry from one to one. The hard part about VHDL is it's very strict about data types, and when it converts to different data widths and the types, you can have unsigned and signed integers in hardware as well, and it will treat it as such. But again, VHDL is very strict about converting it. You have to explicitly cast things. Yeah. And again, with another thing I forgot about, FPGAs, you can have arbitrary widths of data. You can have 7 bits, you can have 13, you can have 19, you can have clear up to 500 bits wide. Again, you're not constrained to 8 bytes increments.
One more, and that this is interesting. So if I wanted to get a starter board, which one would you recommend?
Yeah.
This looks cool.
Yeah, there's a lot of great, I think Dan will send me a link at some point for the link to the Discord, but I can put in some good resources if you ever want to learn this stuff. Some great YouTube playlists and other web pages. For the boards, I don't think I have it installed on this computer, but there's a IDE called Ice Studio. It's open source and it's pretty easy to use. And you can get these cheap FPGAs that cost anywhere from $20 to $50. And they have like 1,700 logic elements which it still takes a while to fill up when you're beginning, clear up to like 50,000 logic elements. And they're pretty good boards. One's called the Icebreaker board. And again, I'll put this in the Discord. But then they have the tiny FPGA, which is like $20, but I don't think they manufacture it anymore. It was just like a GoFundMe project that someone did. But yeah, you're looking at anywhere from $20 to $50 to get started with the actual hardware. But you don't need the hardware to get started. You can just run simulations, although it's not nearly as fun as putting on the board and seeing it work. And again, these things don't have they have LEDs and buttons and other ways of talking to computers, but there's not like a digital screen or buzzers, but you can add buzzers. You can add an OLED display to them if you really want to take the time to learn how to send data to an OLED. You can do that.
That's the rabbit hole of FPGAs.
Yep.
You keep buying these little module things.
Yeah.
So you get like a little keypad and you can like plug in like lights and then
Accelerometer and
drawing
yeah.
on your board and you just
A lot of people use them to drive pixel displays. So those pixel matrices, they hook up a lot of those together and they'll drive it with an FPGA. Yeah.
Nice.
Yeah. So I don't know, any more questions or we're going to wrap it up? Okay. Sounds like we'll wrap it up. That's my presentation. Again, it's not really kind of how you do this one thing. It's kind of brief overview because I imagine a lot of people would be new to FPGAs. But this is kind of what they can do, and now you're a little bit more acquainted with them. Hopefully it's not for everyone, but hopefully you enjoyed the presentation. So, yeah.